Brighten, thank you very much for joining us today for the webinar. So we have today Brighten Godfrey, professor at the Civil School of Computing and Data Science at the University of Illinois Urbana-Champaign. He co-founded and served as CTO of network verification pioneer Veriflow through its 2019 acquisition by VMware, now Broadcom. With that, I give you the room, please. Go ahead.
All right, you can hear me okay?
Yes.
All right, so thank you, Ignacio. Thank you very much for the invitation to speak. It's an honor and great to see a lot of familiar faces. Since this is not a conference talk, it's an invited talk. So first of all, let's keep it interactive and feel free to stop me, ask questions at any point in time. And also, since it's invited talk, I think that it gives me license to start with a personal story. So as many of us know, for researchers, picking the right problems to work on can be exciting, but also stressful. And for networking researchers, that stress sometimes creates feelings of anxiety, self-reflection, and a sudden urge to design a congestion control protocol. And I was not immune to this effect, which led to a project called Performance-Oriented Congestion Control, or PCC, with my students and Michael Shapiro's group at Hebrew University. So the goal was consistent high performance, meaning that the protocol would perform well in many different environments. So, you know, we had some ideas we thought were pretty good and tested in many different environments, huge number of tests. The students were amazing. We thought things were pretty solid, submitted the paper, even included the code with the paper. And lo and behold, one of the reviewers, let's just call them reviewer 2, took us up on the offer of trying and said, you know, I can defeat your protocol with an unbounded bottleneck buffer. So how consistently high performance is it then? Reject. Well, I had fallen victim to one of the classic blunders in networking, as they say. The most famous is never think that 32 bits is enough address space, but only slightly less well-known is this. Never assume it's easy to predict what a network system will do when it's deployed. And it's not just me. The field is littered with examples of protocols exhibiting performance that was not totally expected. So in congestion control, for example, BBR version 1 turned out to be surprisingly unfair to loss-based flows, more traditional congestion controllers, grabbing a significant fraction of the bandwidth, even with competing with many flows. A variety of congestion control algorithms perform poorly over low Earth orbit satellite, not because the latency is extremely high, which might have been expected, but because of variations as satellites move. Outside of congestion control in adaptive bitrate video, the community collectively did a lot of work on more advanced ABR algorithms, for example, using learning-based approaches even. But then on a much larger scale real world test, it turned out that simple buffer-based approaches outperformed those more sophisticated approaches, which might not have been expected given the earlier results. And not just end-to-end protocols, if we look at how a whole network system with multiple components works, let's say a large cloud network where you need to perform incident diagnosis. Well, you know, a lot of things happen in a complex system with multiple interacting parts that would have been very hard to predict. And diagnosis can take hours or even days in enterprises, sometimes even longer, to be honest, to figure out what's the source of a tricky problem. So there's many ways in which this fact is true. And I think there's some fundamental properties of networking that make this true. that make it hard, even though we built the systems ourselves, we designed the protocols, yet it's still hard to understand the implications of them. So one reason is that there are essentially always, we in networking are dealing with distributed interactions. We're also dealing with unknown states, both us as the protocol or system designers, but also the protocol itself is perhaps trying to make inferences implicitly without full knowledge of what's going on. And because we're building infrastructure protocols, we always have to keep in mind that we'll be deployed in an incredibly diverse range of environments. I mean, think about the range of environments that, say, the Linux kernel networking stack is deployed from, the smallest embedded devices all the way up to, extremely powerful data center nodes used for machine learning training. So this is pretty difficult, but despite this complexity, on the other side, there's always underlying structure in protocols and in environments because of the algorithms that are running, because of patterns in the workloads. And almost always we have data available about how the system is running. So one of the points I want to make in this talk is that this combination of properties here, I think, creates a domain that machine learning can fruitfully take advantage of. So that's what we're going to kind of be exploring in this talk, the question of whether machine learning can help us understand the systems that we built. And I'll talk about two main examples in different domains: performance diagnosis of distributed applications and robustness of congestion control protocols. And then after that, we'll talk a little bit about what I see as some exciting future challenges. So the first work was led by my student, now Dr. Vipul Harsh, and was primarily done at VMware. So in this domain, we're dealing with troubleshooting incidents in network systems, like, for example, a enterprise cloud. And it's difficult because we're always dealing with a large number of entities, first of all: virtual machines, hosts, flows, switches, complex dependencies between them, applications deployed in different places that are making API calls to each other. And at the same time, we have data, but it's not necessarily, sort of microsecond scale data. It might be more coarse-grained, seconds, even minutes, that metrics are collected so that we can understand what's going on. But we do have these time series metrics at some level of aggregation about how components in the system are performing. So can we automate troubleshooting using this telemetry? Now, we're not the first ones to ask that question. I'll come to that in a moment. But just to be a little bit more specific, what we're trying to do here is performance diagnosis. So let's say we start with some externally observable signal, some problem that the operator became aware of, like there's high CPU on these backend servers and my application stopped responding. Okay, why is that? And what we want to do is be able to say, okay, starting with this problematic symptom, an entity, and a metric, we can infer whatever the root cause was. And maybe in this case, which is actually coming from a real example in an actual enterprise, there's a crawler machine that was issuing flows to a front-end server, and a surprisingly large number of queries at a high rate that was then sending queries to back-end servers, causing high load there, and then affecting other concurrent queries. So that's like a multi-hop chain of causality. And we'd like to, if we can, automatically find that root cause. So at a high level, you can approach this problem in different ways. And there have been some attempts at it in the past that have made some progress. And one of the ways to characterize that is, what dependencies do you assume between entities. It's sort of like, what do you know a priori or based on some data independent of the specific incident about how the various entities in the system relate to each other? So you could assume nothing. We just have like a bag of entities and there's a bunch of metrics, and we can, throw some correlation or machine learning at it and try to figure out where things are connected to other things. You can do that, very general purpose, that's an advantage, but then accuracy is limited. At the other end of the spectrum, you could assume that you know a lot of structure in the system, in particular a dependency graph, an acyclic dependency graph where, say, front-end node is calling certain other services, and those are calling certain other services, and that's the entire system. That characterizes what can affect what fully. Now, the problem is that, as we'll see, it's very hard to describe a system as a DAG. It really doesn't fit. Most systems in terms of how components can affect each other just are not a DAG. So the question is there some middle ground where we can take advantage of some structure in a system to inform learning, but still have it be sufficiently general? And the problem that we're dealing with here is really that cyclic dependencies among entities are the norm. There's two reasons for that. One is that there are actual cyclic interfaces. For example, if you just look at a VM running on a host, the VM affects resource availability on the host, and therefore it affects other VMs on the host. But those VMs, which are also using resources, in turn affect the host. So the causality is in both directions, depending on, through this connection of shared resource utilization. And also, VMs influence each other via flows. There's API calls, and queries from one machine to another both affect what's happening on that machine, and results come back and they affect what's happening on the client as well. So there's frequent cyclic influences, and also it can be hard to infer the dependency direction. This is kind of a separate issue that you can see there's a connection. Like if there's a TCP flow between two hosts, okay, you might say, all right, there's some RPCs probably happening between these microservices. But which is the direction of influence, it might be hard to know a priori, even if there is one. So a natural thing to do there is to over approximate and say, okay, I know there may be influence between these two, but I don't know the direction, so I'll consider both, which then gives us cycles. So we actually looked at this. We took some data from a network monitoring system deployed in a real enterprise, I think about 300 applications, and looked at just sort of what is the natural graph that arises from what you know about the system. And every single one of those applications were involved in at least one cycle. So this might seem like a small technical point, are there cycles or not, but it actually significantly influences the hardness of the inference problem. So how did we approach this? We wanted to be able to handle cycles, but still take some useful information from this dependency, from this relationship graph. Basically, what we built is a system called Murphy that takes as inputs first a problematic system, like some machine has high CPU usage, and it also takes monitoring information. With those inputs, it's going to construct a model of entities and dependencies in the network, use that model to find root causes, and then generate explanations. So in the end, it's going to output something like, there was a crawler machine, and the crawler machine sent high rate of requests to the front end, which sent high rate of requests to the back end, which caused high load at the back end. And that's the chain of causality. Okay, so how do we build this model? So we're not going to use a causal DAG, which assumes too much. We're going to use a more kind of fuzzy relationship graph. And typically this means we'll have hundreds or thousands of entities, starting with the symptom and kind of doing a breadth first search out to some radius as a starting point. Okay, here's the entities that could be reasonably involved that might influence in any way, in general, this particular starting point. So the edges here are defined based on a neighborhood relationship. So for example, if a VM is running on a host, then they're related. And then the host in turn is related to all of the VMs running on it and to the top of rack switch it's connected to. If there's a TCP flow, the source and destination are related and so on. So this gets us a relationship graph that captures the topological structure while allowing cycles.
Sorry, Brighton.
Okay.
A question
Yeah.
from Richard. What is your input data here to infer? Right? Is this log data, I guess?
Yeah, so logs and network telemetry. So actually, most of what we're using it's not logs in the sense of like text messages that are output by programs periodically when some events happen. It's more like time series metrics. So for example, throughput of TCP flows at some time interval across several weeks, just like continuously monitored in the system, or number of flows per second, that sort of thing. CPU utilization, interface errors, right? So these kind of time series metrics is the input. So generally there's, for each entity there, like a flow, there might be a handful of metrics, each with its own time series. So, which means that if we're dealing with thousands of entities, we're talking about, I don't know, ballpark thousands to tens of thousands of individual time series. Yeah,
So
good question.
I had a related question. Sorry, Brighton, I got super delayed with my traffic. I was coming back from somewhere.
No worries.
So with this whole cyclical thing, I wonder whether if you go down one level of abstraction or multiple levels of abstraction, all the way down to processes or even logs that you're trying to track, couldn't you then say that this process only affects this other process in this one way, or this log, the effects of this log can only be seen in this other log type of thing? Is it simply a matter of the level of abstraction, or is it just that you don't know before you have a look at it?
Yeah, that's a great question. So, there's those two reasons that I mentioned that cycles occur. And I think if you go, way down in your level of monitoring, maybe in levels of the stack, but also in time granularity, you might, I think you would in fact be able to differentiate and disambiguate some events and say that, okay, the interaction is, this way, not the other way. You could, for example, see exact timing of certain events. Imagine you could like just trace every line of code, right? You could see, this thing caused this other thing. We can make the graph, reduce the graph to have that edge point in only one direction. So some of that would be improved. The challenge there is overhead in monitoring. Usually you don't get that level of detail in practice. And the other thing is, in some cases, the causality really is bidirectional, right? Like these resource contention type things. If multiple entities are sharing the same resources, then they affect each other, basically.
Sure.
And so you get cycles for this reason.
Yeah, I see. Yeah.
But it would help, right? If you have, more fine-grained monitoring. Other questions right now? All right. So now we've got this graph to start with, and we need to build a model to understand, to predict what is the cause of some anomalous metric. Okay. We need to infer the root cause. So we're going to do that with a particular method that's a kind of learning called a probabilistic graphical model. And what we do is we learn a joint probability distribution of all entity metrics. So within that scope of hundreds or several thousand entities, we're going to learn from data how they behave and influence each other in general, not, or I should say in kind of recent time, including during the incident in question. So let's take this toy example. There's this small topology, and let's say each one of these entities just has a single time series metric or a single metric. So we'll build what we call what's called a Markov random field that's learned via historical data prior to the incident. So to be concrete, we take like 2 weeks of data, these time series metrics, and we're going to build this probabilistic model. And basically, because it's a graphical model, what it's saying is that the graph lets us restrict what we need to look at. A node can be influenced by its neighbors, but nothing other than its neighbors. So conditional on the value of the neighbors of B, A, C, and E, what's the likely value of B? Okay, so that's like one component of the overall model is the per node model. Okay. Once we have that model learned as a Markov random field from data, that kind of tells us how things affect each other. And then we use it in a counterfactual way to try to infer root cause. So what I mean by that is, what we're asking is, would changing the value at, let's say, A, resolve the high metric value at D? Okay, so what we do is we pick a different value than the current value at the time of the incident for A. So it's A star. Let's say, it's requests per second at A, and we cut that in half. Okay. Then we resample the neighbors from the probabilistic model, assuming the new conditional value of A star here. So then we've got a B star, and we propagate that resampling through the other neighbors until we get to D. Now we know there are cycles, which means there's bidirectional influence. So we can't just do a single path. This is done with multiple passes so that nodes can be affected in either direction. So this is a basic approach that's known as Gibbs sampling. There's a slight modification of it that we're using, but that's the basic idea. So we repeat this several times and it converges. And then we've got a value at D. And then you repeat that whole process multiple times, and you can get multiple values at D, or at least several values at D. And you can see if, okay, did the distribution shift after the change at A? And so if D prime is less than D substantially, then we say A is a possible root cause. And then there's another iteration over all possible entities to check them one by one and see what has likely higher influence. So what that does is it gets us several potential root causes that bubble up to the kind of the top of the list as most likely. Oops, excuse me. And then comes the last stage to generate explanations. And what we do there is basically trace through the graph with a small kind of state machine model of what can influence what in principle, not in any one given particular setting, to be able to find these paths and then generate that kind of linear chain explanation. So without going into too much details there, and I'm skipping over a few things, that's the basic idea. Okay, so let's take a look at how this works experimentally. So we did a few different types of tests. The first scenario is a system in which there are cyclic dependencies. So this is a microservice deployment where there's some root cause that's high response time from client one. And it turns out that client one's requests are basically influenced by client two's requests through a shared backend service. But this dependency, as you can see here, tracing it through, there's a cycle of dependencies. If you will only kind of look at a DAG in one direction, you would not see this. You wouldn't be able to trace it back. So this is kind of the scenario that we expect the system to excel, and it does. So just as an explanation, each of these systems, including the past work we're looking at, it can output a list of likely root causes, in some ranked order of likelihood. So we're looking at the top K here. So as a function of K on the x-axis, we can see what's the accuracy. Was the true root cause included in those top K? So of course, that's going to be an increasing function. And Murphy is able to handle this scenario decently well. So the root causes are the majority of the time, like 90% of the time, in the top, 5 or 6 roughly entities, or sorry, possible root causes. So that gives the operator something that they can reasonably check, a few starting points such that they'll probably get a good idea of what's going on pretty quickly. Now, if we look at a scenario with no dependencies, then SAGE is another technique that performs pretty well in this case. And SAGE was specifically designed for this directed acyclic graph environment. So also not surprising that it performs decently well here. But Murphy is still doing a kind of more discriminating analysis, even in that case. So we also looked at production incidents. So this is data taken from a real network monitoring product deployed in an enterprise. And we extracted 13 real incidents where we had data available, which, by the way, is a lot of work by the lead student, Vipul, who worked on this, to be able to actually find and extract in a meaningful form what was going on in each one of these incidents. It's a lot of time for the operators to figure them out as well. So, so looking at these incidents, we compared the past work that does work for cyclic environments, because that was a requirement for it to be able to even run in this case, and found about a factor of 5 fewer false positives. So that was a promising result. And this technology, a form of this technology, became a beta feature in VMware's ARIA operations for networks network monitoring product. So that's what I'm going to say about diagnosis. Let me pause here for just a moment and see if there's any questions before we go to the second part of the talk.
Yeah, really cool. Just wonder if I could ask about that root cause data, because I've been interested in that kind of thing before. It's very hard to get that data. Where companies are a bit reluctant. Is the data public? Can you say a little more about the data you're working with? Because I've found it's mostly kind of unobtainium,
Yeah, this work would not have been possible without collaborating with VMware. Most of the work was done under the auspices of VMware. Right. So that's really why we were able to do it. I mean, I would not have really been comfortable in doing this kind of work with no real world data.
Yeah, absolutely.
The thing about production incidents is you just don't know what they're going to look like, right? You can invent something that they look like, and it might be completely unrelated to reality. And we really
I was honestly expecting you to do that before you got to the results slide.
We wanted it to be kind of as grounded in reality as possible. There's multiple data sets. Unfortunately, the production data set is not publicly available. That was taken from a real deployment of VMware ARIA operations for networks. Mm-hmm. So it was, quite interesting, valuable data. We did create some large data sets from a synthetic Kubernetes deployment. with microservice applications from a project called Death Star Bench. So it's real in the sense that they are simple but actual running applications where we injected real faults like noise in the CPU resource availability, for example.
Yeah.
And collected that data and logged it. So that data set is publicly available, and I can you may be able to find it with the right searches, but you can email me after and I can point you to that data set.
Cool. All right. Thanks very much for your answer. Appreciate it.
Sure.
Very cool stuff. I was wondering, well, I saw that the performance is actually quite good, because when you were showing it at the beginning, if I understood it correctly, you build a graph, right? And you know the entities in the graph, but the relationships are a little bit harder to establish, right?
Yeah, the relationships, the sort of high-level relationships are known in advance. Like this VM is running on this host. We know that, we can see that directly. So that's unambiguous.
Oh, okay. So because from what you said, I thought that there could be many different types of relationships that you could establish between the different entities in your graph.
There are, yeah, I mean, there's, in terms of what's happening in the system, there are many different kinds of relationships. But we can see that there is a relationship in certain ways, right? Like we know, for the entity types that are being monitored, we can see these are the entities, this is where they're located, and this is who they're talking to, okay? Now, that doesn't necessarily let you go finer grained. Like, for example, if your monitoring data includes VMs and containers, but not processes, then you're not going to be able to see, what a specific process is doing. It's kind of lumping that all together. If your monitoring system is missing data, like, some chunk of network flow monitoring was just dropped from the system, or for some reason it was, there was some data collection issue, then that would be a problem. But you can see sort of, with some degree of reliability, here's what your things in question are, here's where they are, and here's which ones are communicating.
Right.
I don't know if that was answering your question.
Yeah, well, that was preemptive of the question. What I was actually wondering is if you could run on different graphs to see if you can find better graphs that allow you to achieve higher performance. But at the end, I was quite surprised to see that performance is actually pretty good. So I'm not sure if the effort would be worth it. But when you were saying about the difficulty of establishing these relationships, I was thinking, well, you could just produce a bunch of different graphs that somehow create different relationships based on the data that you have, and iterate through them with the model to see if you can improve. And once you do, to try to reverse engineer what the reason is.
Yeah, that's an interesting idea. We didn't really think about iterating over different candidate graphs. That's an interesting idea. I wonder if you could even sort of use a technique like that to infer what actually is the graph of influence.
Yeah, exactly.
There's some other work that tries to infer some sort of causality graph or relationship graph in cases where it might be fuzzy. So that could be interesting. We did look at what happens if you remove some edges from the graph, if the graph is imperfect. So that's the one sense in which we sort of tried out different graphs. Not that it would be run live in the system, but just as an experiment, what happens if we give somewhat incorrect data about the relationship graph to the system. And performance does degrade if there's missing data. It can be somewhat graceful depending on how much is missing, but yeah. But that data is in the paper if you're interested in it.
Nice, thank you.
Yeah, but interesting idea. I think that's an interesting idea to kind of go backwards and infer the graph by trying out different candidates.
So there's actually a class of programming languages, probabilistic programming languages, which you can use to do these kinds of inference going backwards and going forwards, what if scenarios and things like that, like Turing and Web PPL and Stan and those kind of languages. And I believe they are quite production ready these days. So might be an interesting idea to have a look at that as well.
Oh, that is interesting. Yeah. Cool. All right. Well, let's go to the second part of the talk here, which is moving from diagnosing clouds to now individual protocols. So we'll talk about robustness of congestion control protocols, and this is work led by Shehab Sarar Ahmed, a PhD student, and with a bunch of other very smart folks. Right. So the question we're addressing here is, how can we be confident that a protocol is robust? As I mentioned, we're dealing with infrastructure in networking all the time, and infrastructure protocols need to perform reliably, but the internet is a huge, diverse, complicated place with, multiple orders of magnitude of range of kinds of access to technologies, bandwidths, latencies, number of intermediate devices, time varying network performance. There's a lot going on here. So how do we know how a protocol will perform before we deploy it? So we can test. We can either emulate manually constructed test cases, we can collect traces of real world performance and replay them in emulation in a test environment. We can do roll something out in production and do A/B testing for the production workload. So these are all useful things that should happen, but they're good for typical behavior in known environments. What they're not good for is telling us what we don't know, what could happen in environments that we're unaware of. So, just looking at the set of all possible environments, they have low coverage of those environments. So the question is, can machine learning help us? And usually we use machine learning in systems to make better choices and perform better. But here in this project, we're going to use it in the opposite way to make systems perform worse. And what I mean is that we're going to use machine learning as an adversary. And this is a place I thought it was appropriate to use a ML generated image. So this is Gemini's idea of an evil neural network. All right. So what we're going to do is use a machine learning model that we train the model to generate environments that cause a system to perform poorly. Okay. And by doing that, we can maybe understand what are the limitations of this particular protocol, in this case, congestion control protocols. So just to be a little bit more specific, we build an automated framework for adversarial testing. And how does this work? The adversary is going to generate network environments, which we then run. We execute a protocol in that environment, and we get a score, like throughput, latency, loss rate, whatever you're interested in. And that score generates a reward for the adversary. So the reward is high when the performance is low. This is a training loop. So we're going to train the adversary to generate better and better environments, or I guess depending on how you look at it, worse and worse environments. And it's not generating environments that are just generically bad. It's tailored to the protocol under test, right? It's being trained to figure out what are the weaknesses of that specific protocol. At the end of this process, we'll generate environments and the associated scores that are particularly adversarial. Let me give you just a little bit more detail about each of these steps. So what is a network environment? We're basically emulating a single, or as we'll see, multiple parallel bottleneck links with flows going over those links. So that bottleneck link has a buffer size. There's a data transmission length of the flow going across it. And then there's time varying parameters. So there's a time series of a latency and a bandwidth for certain duration, and then another latency and another bandwidth for a certain duration, and so on. So by creating multiple of these time series entries, the adversary can generate some pretty complex network performance characteristics. So then we go to execute, and the emulator is an extended version of Mahi-Mahi that's going to run the protocol under test. Now, if you were the adversary, if your goal was to cause a transport protocol to perform badly, what would you do? What network environment would you generate? Any suggestions?
Something with dynamically varying conditions.
Okay, yep, dynamically varying conditions are often hard. But if all you want to do is make the protocol, have low throughput, what would you do?
So Richard says high variability congestion to empty quickly, high number of contesting flows.
Yeah, so high number of that would do it, which is kind of saying there's not much available bandwidth. So in fact, you could do something even simpler, which is just set the bandwidth to 0 or set the loss rate to 50% or 100% or something like that. So we need some way to kind of rule out these trivial cases. So the way we do that is we not only have the target protocol, but we have a reference, okay? And the reference can be either a definition of the optimal if you know it, but the optimal might be unrealistic to achieve or even hard to compute in some cases. So the reference can be a concrete execution of another protocol. And what we're looking for is a gap between the target and the reference. Okay, so that's what the score is basically defining. The score is going to be the performance of the reference minus the performance of the target divided by the performance of the reference. So for example, if the score is 0.3, let's say, then that would mean that the target performs 30% worse than the reference in that particular environment. Okay, so those scores get fed as rewards to the adversary. We've tried several different adversaries using genetic algorithms and reinforcement learning, and they actually perform, just differently in some cases. Reinforcement learning isn't uniformly better or worse, and part of the reason is we're dealing with a relatively limited number of trials because we're doing actual protocol executions, right? This is running an emulation. We're not dealing with training a deep neural network on, say, like the entire contents of the internet or that, that scale. There's a relatively limited number of trials, and that may be one thing that's causing genetic algorithms to be competitive. Okay, there's a few more design decisions I'm going to skip over, but pretty important things are: how do you choose the granularity of the environment representation? How do you deal with experimental noise? And do you want to use an online adversary that's sort of adapting the environment as the protocol is making its decisions, or an offline adversary that generates a concrete trace end-to-end, start to finish, and then the protocol executes across that? So what we're using is the offline versions, which is better for reproducibility, among other things. I'll talk quickly about 3 use cases. First, just measuring basic robustness of protocols versus other protocols. Second, understanding whether a multipath TCP is actually better than running over a single path. And third, regression testing. So these are 3 examples where we think that this kind of adversarial environment generation could be pretty useful in practice. So this first case is robustness with other protocols. So the question here is, how bad can a protocol be compared to other protocols? And it's kind of a competition, but it's not a competition in the sense of 2 protocols running together and looking at fairness. They're running independently on the same environment. You run one protocol on the environment, see how it does, then run the other protocol in the same environment, see how it does. So we're using iperf to send traffic. The goal here is just throughput to keep it simple. And we tested all of the Linux kernel TCP versions. There's 17 of those, which means there's 272 adversarial tests for different target, reference protocol pairs. So that's a lot of tests. If you run all of those, then it looks like this. So this is a matrix comparing the robustness of all protocols. So the row is the target protocol, and the column is the reference protocol. And we're seeing scores here numerically. That's the score that I mentioned before. So for example, this 0.66 here for cubic tested versus BBR means that the adversary found cases where the advantage of BBR over cubic was 66%. So roughly, BBR was a factor of 3 better in some environments. On the other hand, the adversary also found cases where cubic was a factor of 10 better than BBR. That's what that cell means. Okay, so a lot of numbers here. You can maybe pick out some patterns. I think there's a couple interesting takeaways here. First is, what would be the point of this? Why would you use something like this? We think that the extreme points here might reveal bugs. And in fact, we found multiple suspicious issues, including potential kernel bug dealing with reordered packets that's kind of in the process of being validated. So we think that's a potential valuable use of this. There's another philosophical point I want to make, is that, if you look at these values, they're all positive scores, which means that all protocols outperform all other protocols. To put it another way, for all protocols A, B, there's an environment where A outperforms B, and there's another environment where B outperforms A. So this is kind of a quantitative illustration of how difficult congestion control is, right? So all of these protocol implementations, there's no sort of like uniformly clear winner that's always better in all cases than any other particular protocol. So maybe this kind of partially explains the hundreds to thousands of TCP congestion controllers that have been proposed. So if you take the average of the rows and columns, you can kind of generate an average throughput robustness. So that's what we're seeing on the y-axis here is the robustness score, which is the average score of a protocol when it's the target. And the x-axis is the mean score as a reference. So roughly this is saying, like, if you're in this region, you have good robustness to a range of environments. If you're in this region, then you're kind of like a good specialist. You excel at certain environments where certain other protocols might not perform well. So there's some interesting patterns here and some definite differences between protocols. This is only for throughput as a metric, but it might be relevant, say, if that's what you care about for, let's say, video on demand, and it's really a throughput thing, not a latency thing. Robustness like this might be useful to, for example, fall back from one protocol to another if you notice that there's poor performance. We've got about 5 minutes left. Do we have a hard stop at the top of the hour, or should we go like 5 minutes over?
I think it's fine.
All right. I'll try to
people
keep
have to run and have burning questions, they can throw them before.
Sounds good. Yeah, feel free to interrupt me. So I'll go through this last bit kind of quickly, but another use case is that when we're developing a multipath TCP protocol, it should be that 2 paths are better than 1, right? Like if you give MPTCP one option, adding a second option, you would hope that performance only gets better and it doesn't make performance worse. So does adding a path ever significantly worsen performance? So we did this, and so now it's a multipath test. And so the target is a multipath protocol on both paths, and the reference is now the same protocol on just one path. So we tested 8 protocol variants of MPTCP, as well as a user space multipath protocol called D-channel from our group. So there's 8 different protocol variants here. So how many of these would you guess actually met the property that 2 paths are always better than 1? Any guesses? Yeah, none of them. They all have cases where they make performance worse by adding a second path. Here's an example of that with the Balia MPTCP controller. In this case, it seems like a delayed ACK causes rate reduction on both paths instead of one. I won't go through spend a lot of time on these since we're short of time. But there's a bunch of examples like that that are potential problems. A third case that we think can be really impactful is regression testing. So when you introduce a new version of the system, you usually want to understand, did I worsen performance compared to the old version? Maybe even you made a change to the code that you don't expect to impact performance in any way, right? So any difference in performance might be interesting. We've tested a few different cases, like testing throughput in BBR v3 versus v1, fairness in v3 versus v1, and also in the MPTCP, Balia algorithm was intended to be an improvement over the Leah algorithm. So here's a case where for those protocols on MPTCP, Leah performs decently well on these 2 links. But on the exact same 2 links, Balia seems to have a significant problem on the second link with, just never finding the right rate to send. All right, I'll quickly mention some related work. There's a couple workshop papers, if you're interested in this, our own, and then and another group that was taking a different approach to adversarial testing in Hotnets a couple of years ago. This approach is related to traditional fuzz testing, right? But fuzz testing, at least traditionally, is good for hard failures like a crash. Here it's a bit different flavor because we have a continuous performance domain. And we're learning, we have the opportunity here to learn a gradient, basically use a gradient-based method to help us optimize an environment. Another approach to this that I want to mention is formal verification. I think it's a very interesting approach in some of Venkat Arun's work to formally verify what are the worst cases, what are the extreme cases that a congestion controller could encounter. So there you get mathematically complete coverage, but you need a model, right? So that's kind of the trade-off. We wanted to be running with real deployed code. Okay, so just in a couple minutes here, I will wrap up with some thoughts on what I see as future grand challenges. And the theme here is moving from understanding systems to then acting within systems. And if, I want to go back all the way to that project I mentioned at the beginning of PCC, congestion control. And so why is it that high performance congestion control is so hard? One is that it's a fundamentally hard problem, as we kind of saw illustrated quantitatively. But another is that traditional congestion control architecture makes it even harder. All of these traditional congestion controllers use handwritten heuristics that are basically hardwired control actions. When you see a certain event, you take a certain action, right? Let's take just one of those particular events, a packet loss. The problem is that there's many different underlying conditions in the network, and they have different associated optimal actions. Like it could be that this flow is causing most of the congestion, in which case you'd want to decrease a lot. Or it could be that there were just some microbursts, and then you'd want to decrease a little your rate. Or it could be that there's another flow congesting the network, in which case you might want to ideally maintain your rate. Or it could be that there's random non-congestion loss and there's actually spare capacity, you should increase your rate. All of these underlying conditions, they have different optimal actions, but they all produce a packet loss. So there's no way to look at just one packet loss and say, given that event, I know the right action. There's no mapping that works there. What could we do instead? Well, the network basically is opaque. We can't see what's happening inside it, but we can send it some rate and see the result. And we can try out different rates and see the results of those, right? So taking just one of those, if we send it some rate and we see the result, we can then give a utility to that, right? And if we do that, we're starting to rephrase the problem in a way that it becomes amenable to learning, right? So we can send it one rate and see, no matter how complex the underlying network was, sending at that rate definitely produced that particular utility, at least at that moment in time. Okay, then we could do that multiple times. We could send at one rate, get a utility, send at another rate, get another utility. Compare them and just move in the direction that makes us happier, right? So this was the basic philosophy of the PCC approach, that we could observe real performance and then, using a learning-based algorithm, associate actions with specific performance outcomes, with observed performance outcomes. Okay, so in the case of congestion control, you could try sending it 95 or 105 megabits. And then if the true underlying cause inside the opaque box there is that this flow is causing most of the congestion, well, moving to a lower rate is going to decrease the probability of packet loss and make us happier. On the other hand, if it was random loss, decreasing the rate won't affect that rate, and actually increasing the rate ends up making us happier, and we'll move in that direction. So that's one example that I bring up because it's an example of a larger principle where there was like a hardwired human-written heuristic that was not data-based. We have the opportunity to take these control actions and make them more based on experimental reality, you might say, or another way to put it is learning from data. And that's true not only of congestion control, there's rate adaptation in the application. In the service layer, there's request routing and overload control. In the network layer, there's the transport and network layer, there's congestion control, network interface card, resource sharing, prioritization, physical rate allocation, and that's within one host. If we then move to the a cloud environment, there's scheduling and auto scaling and resource harvesting and so on. I'll mention as an aside here that this particular vision of taking the very large number of human-written policies and making them more learning-based is the goal of the LDOS project, Learning Directed Operating System, which is an NSF Expeditions project led by Aditya Kella, in which I'm also a collaborator on. That's within the scope of an operating system. But there's a broader possibility here. And what everyone would like to do is really, get to the point that we have like a self-driving cloud, as illustrated here. That's a cloud driving itself, where it can, self-optimize, self-repair, self-diagnose, and so on. But, the challenge really here is that how do we do that in a robust way? Automation is always risky, right? Automation is one of the root causes of pretty much all of the large outages that you see at major clouds. But ML-based automation might be even riskier, right? Because there's that uncertainty of behavior outside the training regime. There's a lack of intuitive understanding by the operator or theoretical analyzability in many cases. I will say, though, that there's some interesting, promising approaches emerging. And this is all work that's kind of caught my attention. It's pretty interesting. None of this is my group's work. But one approach is machine learning, but in a hybrid way with help from a classic controller. Another approach is formally verifying the ML model will preserve certain properties. And another direction is in explainability. Allowing the user of or the deployer of a learning enabled system to get a human level explanation of why it's making a certain decision. So all of those are pretty interesting directions that are promising, but I think there's a grand challenge here that's broader, and there'll be some very exciting opportunities. So I'll leave you with that. These kind of principles, I think that first of all, the fact that network systems that we deal with have this property of complexity with structure, which means that there's many opportunities for machine learning to understand and improve network systems. But a key challenge is going to be learning with the robustness that infrastructure needs. So thank you very much for your attention. If you're interested in adversarial testing of your protocol, let's talk. We have adversarial testing code ready for you to try out. And I'd like to thank the lead students on the projects I talked about, Shehab and Vipul, for their contributions, including some of the slides, as well as useful comments from Francis Yen, Eshan Gupta, Amar Tahir, and funding from NSF. So thank you all for your attention, and hopefully I didn't go too dramatically over time. I'm happy to stick around and discuss. Thank you.
It's
Thank you very
a
much,
Friday
Brighten.
afternoon, so
Little
I'm
presentation.
assuming most of us don't have too many meetings waiting for us.
That's an advantage.
So any questions, anyone?
If there are, maybe I kick off with one. I was wondering, what you have done is for testing for congestion control. Up to what extent could you extend this to other protocols?
Yeah, we have experimented with ABR video, and it's a very similar kind of pattern. Some experiments with load balancing, but no conclusive results there. So I mean, it's a framework that I definitely think that there's opportunity to apply that approach to other cases where you have like an unknown environment, basically. So if you have suggestions, I'd be happy to hear them.
Oh, we'll take note of that. Yeah, Richard.
Cool stuff. Cool stuff. Can you pop up your little slide with the different types of TCP and robustness? I was quite interested in that.
Yes, let me go back to that.
It's a long while since I've done TCP research. I'm probably pretty out of date, but I was kind of surprised. It was the one where you had a quadrant for robust and a quadrant for, you know the one I mean? Yeah. I was looking at this, and I'm probably a bit out. I had to look up what's Hibbler. That's because I don't know. And that's the one that's marked as the one that's like robust and really robust, great specialist. But I mean, that's not deployed by that many systems, is it? It's Google's telling me it's like satellites and things with high delay. I'm wondering why it's doing so well.
That's right. Yeah, and so it might be that because it was kind of designed for more extreme environments. That might be why it's performing better here.
Yeah. I'm wondering if it's just kind of because it's for high delay comms. It just kind of, they used to say, takes a licking and keeps on ticking. It does its thing, and comes out as robust because of that. It's fascinating because all the ones I expected to be good were not so good compared with it.
It's also worth noting here that the goal in this particular test was just throughput, right? And some of these protocols do try to balance that with latency.
Yes.
So one could produce another version of this graph for a different objective, which is something that's in progress.
It really
depends on what your objective is.
I would not have predicted it as the winner for sure.
Yeah.
And New Vegas seems to suffer in correspondence to Vegas as well, which is surprising.
Yes.
Yeah, lots to see there. Thanks very much.
You're welcome. Yeah, thanks for the comments.
Any other questions?
Very cool stuff. Thank you very much. I think
Thanks, Hamid.
just one minor thing that because at the end of your talk you referred to something which It's kind of referred to as RLHF, reinforcement learning with human feedback. I think the one problem, and this is very popular in the telemetry world, but the problem in this case is that, especially the first part of the talk, this hugely depends on really corner cases, which are getting more complicated, and it needs somebody like, I don't know, Aman Sheikh or somebody who has that sort of longitudinal understanding of the network to kind of dig through and find this. So it becomes very difficult to actually get this human feedback. But I think it's a super interesting area of work for sure. Yeah. So I hope you can take it up.
That is, yeah, that's definitely challenging. Yeah, for diagnosis particularly, and overall challenges that you're dealing with exceptional cases. And they're all their own special flowers. Not, to an extent, many of them are their own special flowers.
Definitely. Thank you very much.
Cool. So if there are no other questions, then I guess thanks, Brighton, for the talk. And sorry, I was late. I had something in Space Command, and then I had to be driving back, and there was some kind of traffic delay as well. So
no worries at all. Yeah,
looks
thank
like
you. Great
guys managed to
discussion.
start. Yeah. Cool.
Yeah,
Enjoyed
thank you
it.
very much, Brighton. Very cool stuff.
Thanks a lot.
Thank you.
Thanks
Bye,
again for
everybody.
the
Have a nice
invitation.
weekend.
Take care.
Hope to
Bye.
see you in person next time. Bye-bye.
Indeed. Yeah.
Have a good
Bye.
weekend, everyone.
Great weekend. Bye.